For our first practice problem, you have a solid 5 Newton globe. We can think of a globe as being a solid sphere. So it has a weight of 5 newtons. It has a radius of 0.5 meters. It is going to begin at rest. That could be a regular velocity. It could also be an angular velocity, depending on where the problem takes us. And then we find that a horizontal force of 15 newtons is applied. Tangentially to the globe. So this is the information that we begin by knowing. Question 5 asks us to determine the angular acceleration of the globe. So keep in mind that angular acceleration is alpha. We're going to look through our equations and see what equations we have that include alpha. So I find that these are the different equations that we have on our formula chart involving alpha. I'm going to look through the variables that I know in order to determine which equation will be useful. So far we have no indication of time, nor do we know how many times the globe is going to spin around. So I think I'm going to base my information on our bottom equation down here. And I'm also going to recognize that torque is a perpendicular force and a radius. So I believe that this equation will be my most beneficial equation. And I'm going to recognize that since it's a solid sphere, I can determine the moment of inertia of that sphere. Take some time, substitute these equations into each other as necessary, and let's determine what our alpha will be. I find alpha to be 147 rads per second. I did this by recognizing that the 15 Newton force was the force applied perpendicular to the 0.5 meter radius. I determined that my moment of inertia of the solid sphere would be 0.051. Though they didn't give me the mass, they told me that it was a 5 Newton weight force. So weight divided by gravity would give me my mass, and then multiplying by the radius squared. And a solid sphere has a factor of 2/5 as its for its moment of inertia. Next, we are asked to determine the angular velocity of the globe after a 4-second interval. So again, I need to refer to my equations and see what my possible choices are for determining my angular velocity. I find that these are the equations that have omega final in them. When looking at the variables that I know, I feel that this will be my best selection, being as I don't know how many times the globe has spun around, which would relate to its angular displacement. I calculate my final rotational velocity after 4 seconds to be 588 rads per second, when I recognize that I had an angular acceleration from our previous problem of 147 rads per second squared. Next, we are asked to determine how much kinetic energy the globe has. Well, the kinetic energy could be translational or it could be rotational. Recognizing that it's a globe, it will spin in place rather than moving forward as it rolls. So I won't need to consider translational kinetic energy, but I will need to consider our rotational kinetic energy. The equation for rotational kinetic energy was 1/2 I omega squared. We should previously know the I, because we needed that at an earlier point, and we just calculated the rotational velocity after 4 seconds, so we also know that component. This should be a simple equation where I'm able to plug in my variables and solve. I calculate that the rotational kinetic energy of the globe after 4 seconds would be 8,820 joules. Again, recognizing that we previously learned the rotational velocity was going to be 588, and we learned that the solid sphere globe would have a moment of inertia of 0.051. Next, we're going to look at the relationship between rotational kinetic energy and translational kinetic energy of a snowball as it is thrown. So we're asked to determine the ratio, that would be a fraction, between the rotational kinetic energy, so that will go on top, and the translational kinetic energy, so that will go on bottom. We know that the equations for each of these and they gave us some information in the problem. They told us that the radius of the snowball was 3 centimeters, which we'll probably need to convert. They told us the velocity of the snowball was 30 meters per second, meaning that is our translational velocity. And they told us that the ball spins about its axis at 75 rads per second, which would be our angular velocity. I'll also recognize that a snowball is a solid sphere if it's tightly packed, meaning that it will have a moment of inertia of 2/5 mr squared. Now, I might feel like I am missing some information, perhaps some maths. You can either make one up, or we can recognize that when we begin to substitute in our equations, like our moment of inertia, some of these variables are going to cancel out. So I won't really need to use the 1/2, being as that's consistent in both equations, and both require some amount of mass. So a simplified equation shows us that we will not actually need those masses in order to calculate this ratio. After substituting in my variables algebraically, I learned that the rotational kinetic energy of the snowball is 2.025 joules, and the translational kinetic energy of that same snowball is 900 joules. So therefore, they have a ratio of 0.00275% of its energy essentially being rotational compared to that translational. Next, we're going to look at question 11 of our packet, where we consider a figure skater who rotates on the tip of their blade of their skate. They have arms that are 1 kilogram each, and their arms are pulled toward their body so that they are 0.5 meters from the axis of rotation. So our skater initially looks something like this. We also know that initially they have an angular speed of 2.5 radians per second. And the skater themselves, or their central body position, has a moment of inertia of 10 kilogram meters squared. This would mean that so they're going to be moving their arms, but the head, body, legs, the parts of their body that aren't going to move much during this situation, this section has a consistent moment of inertia. Now, because they're acting as a whole person, we'll need to consider what the moment of inertia is for the body plus the moment of inertia for their arms as well. We're also told in the problem that at some point they move their arms outward to a position of 1.5 meters from the center of rotation, which would be a really tall person, but we're going to go with it. And as a result of that, we want to figure out what is their final angular velocity at this point. So the skater has not changed position. They haven't changed their potential energy, but they've obviously changed their speed. meaning that they've changed their kinetic energy. So as a result, what that tells us is work was done in some form or fashion. When work is done, we find that it is easier to apply the law of conservation of momentum to describe a situation. So regardless of which body position the skater is in, they're going to have the same amount of momentum. On one side, which momentum is the moment of inertia times their angular velocity. So we know their initial angular velocity. We're trying to identify their final angular velocity. We need to get a better idea of their moment of inertia. And so their moment of inertia is going to be 10 plus whatever the moment of their arms are, which will be different from the beginning to the end. So how do we determine the moment of inertia of their arms? Well, when they're spinning, what's effectively going to be happening is their arms are going to be moving around in a circle with that mass being outside of their body. So we have to decide what kind of shape that relates to. And when in doubt, if we're not sure what it is, we're just going to use the mr squared. Part of this is going to go along with the idea that the body position isn't changing. So if we had a fraction in front of either of the equations, recognizing that it's going to be the same initially as it is finally, that fraction component's going to cancel out. So what I really care about is the moment of inertia that I start with, how much mass do I have, times the radius that I was given. So in this case, each arm has a mass of 1. The radius when we started was 0.5. We'll square that. And then don't forget that we do have 2 arms, so I need to think about that component. When we finish, same 1 kilogram arm, but now our radius is 1.5. And we do still have 2 arms, hopefully. So we'll first calculate the moment of inertia of their arms, add it to the body, plug into our conservation of momentum equation, and we should be able to calculate for that final rotational speed. When I finish my calculations, I determined that the final angular velocity is about 1.81 radians per second squared. If I want to ask myself if this is a reasonable thing, I'm going to think back to my notes in the idea that we're having to maintain our momentum. So when our arms moved out, that increased the moment of inertia, which would decrease our speed. And in the real world, I definitely recognize that when the skaters have their arms further out, they go slow, and as they pull their arms in, they tend to increase their rotational speed. So this makes logical sense that my final angular velocity is less than my initial angular velocity. For our last question, we've been asked how much work was done by the skater. Well, let's recall from our Unit 3 that work is the change in kinetic energy, or it is the force times the displacement along the same plane. Being as our skater hasn't moved, I don't really need to consider this component, but I can consider the fact that they changed velocity, meaning that the work will be equal to 1/2 I omega squared with the final velocity minus the initial kinetic energy, or 1/2 I omega initial squared. I can plug in the variables that I've already found from the previous question and simply solve. When I finish my calculations, I find that the work done by the skater was negative 9.0525 joules, where they lost or slowed down their kinetic energy by just over 9 joules. This concludes our individual practice of rotational energy as well as rotational momentum. We have remaining homework questions that relate to these in quest homework number 8 that I encourage you to begin.